Yeah, can we assign? Can I just like overload? No. Oh, well, look at that, an error. All right, this is neither here nor there. Where were we? Okay, so this should be a little bit easier. I would like you to implement 6 through 10 using, I didn't talk about the mathematics functions, sorry, but these are the same as the ones I showed you before. For math nerds, minus is actually monus because we can't do negative numbers. I mean, you can, but I'm not. We're just doing natural numbers. So see if you can implement 6 through 10 using, be creative. Use any combination of the above functions. Test using toInt. Like I can say 20 is, the parentheses get a little hairy, unfortunately. So I could plus, I don't know. Yeah, implement. Actually, I should do it like this. I'm not going to do 20. 12 equals, yeah, molt 3, 4. There you go. Then I can test it. Magic. Anybody have a good 6? I'm not trying to trick you. Any 6 is fine. What's this? What can I do for 6? Yeah, plus 3, 3. I heard that. Right. 2int 6. How about 7? I know I'm insulting your intelligence right now, but. Oh, okay. Yeah, sure. That also works. Yeah. Now that we have a 6, we can create a 7 using suck function. 2int. Right. Test. Right. Doesn't matter how you do these. I mean, I just invented some that look like that. You do exponentiation if you're a fancy person. Okay, so I'm actually surprised that there have been some questions about reduction steps. So here are some reduction steps for just plus 1 and 2, right? 1 plus 2. This is what reduction might look like. I know this looks like lunacy, but I'm pretty sure, and again, I tested these to avoid humiliation. If you type any of these, they're all equivalent, right? I said referential transparency. I forget that term. This is the point of functional programming, right? As we perform these reduction steps, these expressions are all equivalent. They all are the same value ultimately. Some of them are reduced. Some of them exist at different stages of reduction, but they are all the same. And no matter which one of these you type in, you get the right answer. They're identical, right? It's just ultimately when we plus 1, 2 is identical to 3. It just hasn't been reduced. Reduce it, we get 3. This is what a very simple reduction procedure looks like for the predecessor function. Unfortunately, this function is a little complicated. So you can see that there are many, many steps. But again, if you enter any of these expressions into the REPL, you're going to get the correct answer, right? They're all equivalent. Okay, here's a slightly more challenging exercise. See if you can implement a function for this equation. N plus 5 to the power of 3. I mean, I'll wait a minute or two. If maybe it's too complicated, then we'll skip it. And if you figure one out, raise your hand, and we'll just do it. Well, we can try. Sorry. Molt. You want molt 5?
Literally like molt, and then within molt 5. Or sorry, molt again. Yeah.
Like that? Like this?
No, give me a second.
Okay. Might want to give it an argument. Like func equals n to something. Because we have an argument, right? Maybe like plus like that. You do something with that. think that's right. It's tricky because it's JavaScript and there are parentheses in the order of operations. I understand that. I don't want to waste a ton of time. I really want you to get the concept, not having to solve little puzzles.
Can you put that in and evaluate it on something? Because I got an error that I don't understand.
Yeah, I think, is that, yeah, okay, I'm happy, yeah. You don't have the answers, don't worry, yeah, so. So raise your hand if this doesn't make sense, what I did here. Seriously, if it doesn't make sense. Doesn't make sense? Okay, no problem. So I want to create a function to represent this equation, n plus 5 to the power of 3. So I have this argument n. So I know I'm going to create this function, anonymous function that takes an argument of n, this lambda n. I can start with the first part of the expression, which is n plus 5. So I have to say plus n. This is weird if you work with JavaScript, right? We don't normally use the application operator this way. Right? I've queried everything and I'm partially applying everything. So I apply plus to n and then I apply it to 5. I mean, you could do it the other way around if you needed to. So now I have a function that will return n plus 5. I mean, I can test that. To int, so func5 is 10, right? Okay, that works. Now I want to take that entire expression and I want to exponentiate on it. So I wrap it, right? I make that whole thing the first argument to the exponent function, and I simply apply that, excuse me, I apply that to 3. And that's why that works. So that, I can also use the fancy new operator that we just got last year in JavaScript. That I don't know if has anyone seen this great addition to JavaScript, the exponentiation operator? It's a cutting edge language. Made my little proof a lot easier though. Does it still not make sense, or does that clear it up?
I'm just still trying to wrap my head about when JavaScript evaluation is happening and when we're just doing textual substitution. So I just looked at your toInt function and I'm trying to wrap my head around.
So now I get to say my favorite sentence of the whole presentation. Don't think about JavaScript. I'm just using it as a convenient medium for presenting some ideas.
Can we evaluate things
We're still doing, you can still think of what we're doing as text substitution. The JavaScript implementation isn't not important to me. I'm just using this as a convenient tool to show you how it actually look. I mean, Lambda calculus has nothing to do with computers. But in order to have fun with it and play with it, we need to use a computer. I'm just using JavaScript because it's there. But conceptually, what we're doing is identical. And it actually works. I mean, I'm showing you that it works. Like this idea of text substitution for function application, it works when you're actually using real functions in your REPL. Eventually, you're going to get to the point where I don't know how to explain what JavaScript is doing, because this is like a little bit weird for programming in JavaScript, all those function applications and reduction steps.
Is it correct to say that your utility functions are the only time you use a JavaScript primitive?
Yeah. Mm-hmm. There are no JavaScript primitives here. Everything is functions. Everything. I promise you. Okay. Moving on, we have some comparison functions. They're a little unwieldy. I know they're kind of ugly. They're long. They're in snake case, capitalized. I'm just trying to call attention to them and make them stand out. It doesn't really matter how you write them yourself. So when we have is0, we can use is0 to derive a less than or equal. Once we have that, we can get everything else, right? Now we have a full suite of comparison operators. So we should be able to implement a max function, right? A function that takes 2 values and returns the greater of the 2 values. You can give that a try for a minute. So I guess something like this, right? Take 2 values, x and y, return the bigger one. Any ideas? Anyone have a max function? I mean, I haven't done composition yet. I mean, I guess you could. What did you have?
I was thinking you could do if then else as
Okay.
first function, then pick your x or y, whichever one you want it to be, and then pick greater than or equal depending on which side you want.
You want to do like that?
And then
Can you tell me exactly what to type in?
let's do greater than or equal x and y,
Okay.
and then we will return x else y.
You can test it. That looks like it works.
What if we do 3, 3?
What should a normal max function do for 3, 3? Probably just return the first one, right? Let's see what I did. I used less than or equal, but maybe same. What about min in terms of max? Want to try min in terms of max? Yeah, use the max function. Yeah, sorry. Use the max function to implement min. Two values, x and y. Which one is smaller? So, like this. Oop. Are these a little too tricky? Because,
Add them together and subtract the max.
pardon?
Adding them together and subtracting the max.
We can do whatever you want. There's probably
You got it.
more than one way of doing it.
Either one of mine.
No, I mean, I wrote one, but that doesn't mean it's the only way to do it. So I gave you some primitives, and you can implement it however you like. It's just like a playground. How would I write that? How do I write that? I hope I typed that right. Well, I don't know mine may look similar, it may not. We're so on the same wavelength. How about that? I'm not supposed to say things are easy. I think once you get the knack for this stuff, you're just like putting things together, right? I only have cliches about functional programming, just like everybody else. It's like Lego bricks. We say that, but we don't really know what it means. And I'm trying to demonstrate that, right? We have only functions to start with, and then we start creating names that are convenient for us, and then we stick them together into more complex computations. Function composition is one of the most important concepts in functional programming. And you can do like neat little point-free style things with it. I'm not going to talk about point-free style specifically, but let's say I wanted to create a not zero function, right? And compose just looks like this, right? Two functions f and g, some value x, and I apply g to x, then I apply f to x. This only works if you have pure functions and no global state. And when it does work, it's magical. Now you can start gluing functions together. So I want to create a not zero function. So I compose, I glue together is zero with not. I think that's pretty straightforward, right? Not zero should be the result of whatever is zero returns, and then inversing it, right? Not is zero. That's the function that I want. It's very convenient than just having to write the whole thing over again from scratch. Just using the smallest possible elements and then building up more complicated things. And I can test it. Oop. Whew, thank God, 3 is not 0. Oh, I guess I should be a good developer and make sure that 0 returns false, right? Oh, good. Yeah, no magic here. You actually could type all this from scratch in the REPL without my code, and it would still all work. Here's the fixed point combinator, the Y combinator. Actually, that's a lie. This is not quite the Y combinator. If you recall earlier, I mentioned that eta reduction is, or eta expansion, eta conversion, whatever you want to call it, is not something I want to talk about. It's something that I need to know about, though, when I do recursion, because if I write a normal recursive function using lambdas in JavaScript, I will blow up my stack. Because it evaluates everything, right? It does eager evaluation. It'll always evaluate both branches for a recursive function, and it will go on forever. So I need to do something to prevent the evaluation of the recursive branch unless I need it. So I just wrap it in a kind of dummy function call, and that's what this extra x is doing here. This is a kind of an implementation detail that's not super important, but I will show you how to do this shortly. Now that I have recursion, though, I can start doing some cool stuff. So I can create a modulus operator. I can create division. All right? These are going to start to look really ugly. But even though I'm using functions only and a lot of parentheses, I think this is relatively legible, right? You can read the mod function and the div function, and you can pretty much read it and see what it does, I hope. You can ignore the fix, but if then else, these two, if m is less than or equal to n, then do the first branch, otherwise the second branch for mod. Likewise for div. It's starting to look like a real programming language. Still bizarre, of course, but the cool thing is that it works. So the next problem is implement a function even that given a number n returns true if n is even and false otherwise. And you'll have to use one of these functions to do that. The what?
X is the self function.
I don't think it's useful to think of it that way, to be honest. I'm just wrapping it in a closure so it doesn't evaluate.
But that is the thing we use for recursion.
Yeah. Yeah, technically it's called the Z combinator. It's the Y combinator, but it's for strict languages, right? Because I don't want to eagerly evaluate. Haskell, by contrast, is lazy evaluation, so it only evaluates on demand. But JavaScript evaluates everything all the time. Anybody want to try even? And then odd, using even and composition? I'll give you a couple of minutes and I'll just show them. I actually don't know how difficult these are. I just invented them. Yeah. For even? Okay. Well, probably want, okay, actually. Yeah. Mod. Like that.
And then give that as the first argument equals along with this.
Sorry, like this? Is that right? That didn't work.
You want rule?
Yeah, probably. Damn, I thought it was perfect presentation ruined. But he was right, and that's important. Well, let's try it.
You did say we were skipping type systems.
Yeah, but type systems work the same way. It's also all functions. It's functions all the way down. I thought about trying to implement a type system using just Lambda expressions. No. I'm really not smart enough. I don't even think it would look comprehensible ultimately. What did I do? Yeah, same thing. Slightly differently, actually, but it doesn't matter how you do it. My answers are not right. They're just my answers. You can do either of these and they would work. And as I pointed out earlier, if then else is redundant also. That's kind of for documentary value. What about odd in terms of even using composition? So no arguments, just composition. Just functions glued together. What would be the most obvious way to do this? Huh? Someone raise your hand so I can just, yeah.
Not even.
Like this?
Compose, not even.
Yeah, compose. Or yeah, compose not even. I think that should work. I'm gonna use bool this time. Yep. I know it's trivial, but pretty cool, right? We're in JavaScript somehow. I mean, this is legal JavaScript. I mean, I wouldn't use it to actually build real applications. There are other languages that are similar to this that you might use. Okay, so here's Factorial, right? We've already looked at Factorial in Lambda calculus. Here's what it looks like in our functional language that we're building up. The reduction steps you have in your file look like that. And again, if you cut and paste any of these into the REPL, they should give you the same answer. Doesn't matter which one. They're just reduction steps. They're all equivalent. I'm not doing, this is not procedural programming, right? This is, you might say it's closer to mathematics if you want, but I'm doing that text substitution thing. It's just like a tedious amount of text substitution, right? I don't want to do all that stuff. I really just want to do 2int fact 2 and get an answer. And I can trust that that fact is identical in representation to all that Lambda stuff. I just simply bury that and abstract over it. I mean, that's what we do in programming, right? We create convenient abstractions, and that's all I'm doing. They're just reliable, convenient abstractions. I have no global state. I don't need it. I can do everything with these materials, and that is what I think is cool about this stuff. Maybe going back to the earlier question about what can we learn from Lambda calculus, I mean, this is it for me. It is, in fact, we say, what is the tagline of this conference last year was rediscover the magic of programming. This, to me, is pretty magical. Like on the basis of very few primitive values, you can basically build, you're building inside your browser right now an entire functional programming language, and it's only 1120. And now you can do anything. It's not convenient, like you don't have libraries and stuff, but you can do it in principle. So now I have a little tutorial here if you actually wanted to start implementing functions using the fixed point combinator. This is just a little explanation how to do it so that you can create some things on your own. I was going to ask you to implement Fibonacci. I don't know if that's asking too much. Maybe it's asking too much. You want to try Fibonacci? Raise your hand if you'd like to try Fibonacci. Okay, go for it. Give it a shot. See if my directions are actually useful. I'll give you, 5 minutes or so. I'm so original, right? Factorial, Fibonacci. Your next coding interview, they ask you to implement something, just do it in functions. Probably won't get the job, but you'll get that feeling of superiority that we all crave. But in all seriousness, in programming this way, if you can ignore the syntax, you're really concentrating on the problem, not the language. That to me is also the benefit of functional programming, and this is simply a way of developing an intuition for that, right? I'm thinking about how to solve my problem using my primitive values, and you ultimately end up with a function that it almost looks like a mathematical equation, right? The syntax recedes to the background. If you're using something like Haskell, much more the case than what I'm doing here. But in principle, it is the same thing, right? Like I'm not tricking you. There's nothing in here that's doing the work for you. I have just chosen a system of encoding, and I'm gluing together a bunch of anonymous functions and then saying that the ultimate representation, the ultimate reduction of any given one of these computations is the value that I'm trying to compute, the value that I'm looking for. And it works. It works every time the same way. Whereas if we had some kind of global state, it might not work every time the same way. You can't trust it. So when you have a Fibonacci that works, raise your hand. I'm really excited to see if you can do it. And if you can't, it's okay. This is a very clumsy style of programming because of all the parentheses and so forth. I understand that. Anybody want to give it a shot? While you're waiting, here's another cool thing I did. You can actually go back and forth between, between lambdas and JavaScript values. So I could do this too. Like if I wanted to say 100, I don't want to write I don't want to write math, maybe 1,000. I don't know. I can just say from int, and it works the other way. That's just a convenience. But I can encode anything with numbers, right? So I can also say Steve is that, and I can encode my name in numbers. Still just lambdas. I think it's UTF-8, whatever JavaScript uses. Now if I do toInt on my name, it'll give me, that doesn't work. Does string work? Hope so. Yeah. Okay. So just do I have an argument? Like n? Okay, yeah. Fib equals fix. Yeah. Yeah. Okay. Do I close that one? Probably. I'm doing a branch now, right? So after the one, pardon? Sorry?
One step to the left.
Yeah.
And then X.
Here?
Yeah.
Okay.
And then parentheses. No, the other parentheses.
Okay, let me go back. So just say open parens, close parens. So less than or equal, open parens, x, close parens.
Open 1, close. Open x, close. Open y, close plus.
Sorry?
Factorial.
Like this?
Yeah. Plus. And now we go R. And red. Red.
Oh, pred, sorry.
X. Close. And close and close. And new open. R. Red. Red.
Two preds?
Yeah. X. And then close 3 times. One more.
Okay.
And then call I. Y.
Like that, like, oh, sorry, just probably like that, right?
Yeah.
Yeah.
And then close up a bunch more.
Pardon? Close everything? Like that?
Maybe.
Yeah. Well, did you test it?
Yeah, it works for me.
Yeah, we do TDD in this room. Okay, so what's a good one? What'd you test with?
Try 7.
7.
Should be 13, right? Nice.
I doubt that was easy. I did it in advance. I don't know if I would have been able to come up with that on the spot. There's mine. I did it a little bit differently.
Yeah.
Same. And if you're curious, oh, you know what? Did I skip something with my factorial? Oh, I didn't show you. Okay, so here's the expansion for factorial, by the way. Just to prove to you it's all functions. And this works. I can say toInt, all that garbage, 2, and it's still the same thing.
You do 4?
I don't.
2 is boring factorial.
You know, why don't you try 4 and tell me if your browser doesn't crash?
Okay.
This is like unnatural stuff we're doing here. And here is the expansion for Fibonacci, which is slightly ridiculous, but it also, what did we do? We did 7, right? It still works. I just want to prove it to you. I'm just using functions. I'm not doing anything magical here. You don't want to type all that stuff in, but you could. Still work. But the abstraction is more convenient. So let's move on to data structures, because you can do data structures in Lambda calculus. Here are some pairs. You can do tuples. You can take the first or the second projection of a pair. You can do n-array tuples, so tuples of any length. Now, one little problem here is you can't reuse your first and second functions for a triple. You have to create new ones. But you can create a third, and on and on and on. I think these are pretty simple, right? You create a pair of 2 values, and then you simply map onto whichever one you're trying to extract. I wonder now, on the basis of just looking at the functions, can you implement 4 tuples and the 4th function? I think Fibonacci is probably going to be the hardest thing I ask you to do. Try this. It's helpful for me to know if these things are achievable or not. See if you can implement 4 tuples and the 4th function, 4th projection. So by 4th projection, I mean a function that returns the 4th element of a series of 4 things, 4 tuple. Yeah? You should have it. No? Or did I not? Maybe. Oh, I didn't give you the answer, did I? I'll give you access to everything at the end of the talk. So if you need it for later, you're going to have it. So what's a good 4 tuple? I guess we call it quadruple? Quadruple? So if you look at the pattern of the pair and the triple, it should be pretty straightforward, maybe, to come up with a 4 tuple. Anyone want to take a guess? Anyone have a 4 tuple? I can just show it. I want to move on to lists, and this is not too exciting. But if you just continue the pattern of the triple, right? I used ABCD instead of X, nothing after Z, so ABCD, PABCD, quadruple, and then the 4th. Just like 3rd, but with one more thing. Pretty sure it works. So I can say, I don't know, 4s equals, oh, I probably never typed this in. 1, 2, 3, 4. 2 and 4th of 4s is 4. Okay, so now we have anonymous products. Okay, lists are the coolest things. Wish I had more time for them, actually. On the basis of the list data structure, I suppose you can create almost any other data structure, I think. The list element function is like cons, if you're familiar with cons from functional programming. It adds one more element to a list, the front of the list. But you have to create a list using also, you have to have an element, a cons, and an empty list. Very similar to Haskell, it just doesn't look as elegant. So I can create, I can just create a list and say list element 1, empty list, right? The head is 1, the tail is empty list. For this function, I have to use toArrayInt to translate back into JavaScript arrays, and that works. And you can do more sophisticated ones. You can do, see, they're very clunky to write. Whoops, list element, help me. Okay, list element 2, list element 3, then empty list to close everything, and then toArrayInt. Nothing's blown up on me yet. So raise your hand if you're familiar with Haskell a little bit. Okay, good. So I don't have to explain folds. Well, I mean, I can if anybody wants me to explain fold, I can. There's not a whole lot of time left, and most of the more Haskell-y stuff that is in here will be cool for you if you already know Haskell, and if you don't, I probably don't have time to go over all of it, but we can. So the cool thing about fold is it's a convenient function to use in composition. Fold is like JavaScript reduce, if you know reduce, right? We have a function, and we have a base value, and then an array of values, or some structure with maybe a series of values, and we want to reduce that using the function and that base value to a final sum value of some kind. We can define map in terms of fold. And now we're actually getting into the realm where it starts to become easier to conceptualize these things in terms of Haskell. And I think you could probably almost read Haskell, even if you've never seen it before, just because you've learned Lambda calculus now. So this is a map function defined using fold in Haskell. This one is it has all of its arguments. This one is slightly, it's not point free, but I don't have the x's. This one is normal recursion. So one of the cooler things about the fold function is it has this principle that any function, any recursive function that falls into a certain category of functions that more or less look like this, they have this kind of structure, can be written and represented as a fold, which makes for a little bit more elegant code. So here is this Haskell function represented in our little Lambda language. These are the same. In fact, this is how I write these. I just grab Haskell library code and I translate it. I'm totally cheating. Remember I said earlier, Haskell is just a Lambda calculus. I hope big takeaway is that you should never humor people when they say functional programming and or Haskell are difficult. You have to learn them. They take a little bit of conceptual practice, I suppose. But the basic principles are not complicated. It's just a matter of learning how the abstractions work. I think the JavaScript code that I'm writing, all these Lambda abstractions, it's more difficult to read, right? You have all these parentheses. The Haskell code is much cleaner. So all I've been doing is translating directly from Haskell code into this little Lambda language, and it it completely works. And you can test this yourself. This is another Haskell represent. This should be commented out. That's not going to work. This is another Haskell function, and this is the JavaScript Lambda language representation of it using our fold operator. And you can play with these in your browser. They do work. They worked the last time I looked at them. So see if I have a good example. I thought I had a better example. Oh, here's some examples. Okay, and here's a filter. So like I said, fold is, if you're familiar with reduce, fold is like reduce. I'm sure you're familiar with maps. Here's filter. Okay, we have map, filter, and reduce. That's functional programming, right? That was meant to elicit a laugh or a chuckle. These are the real things, at least. And if you plug these expressions into your REPL, they will work. And this map will actually work more reliably and correctly, more correctly than the JavaScript native ones, because they really only take one argument. Each. They're curried, is what I'm trying to say. Okay, there we go. So I'm folding the plus operator. I'm folding addition over my list of values 1, 2, 3 with the base case of 0, so 1 plus 2 plus 3, right? I'm folding addition over that. 1 plus 2 plus 3 equals 1 plus 2 plus 3 plus 0 equals 6. And you can do a regular map, filter. These things all work. Play with them, type in whatever you want. Create lists, filter, map, fold. It's only 11:40, and I've already created a more expressive and powerful language than JavaScript itself within JavaScript. I mean, you're going to break your stacks eventually. The stuff eventually, like I'm not trampolining, so the recursions will kill you. But I hope conceptually it's starting to come together, right? Now I can do some really cool stuff with my folds. So I'm going to create a function, and equals 2, which is a composition of my and function, and equals partially applied to 2, right? So I want a function that's going to tell me whether or not a value equals 2. Then I create this other little function, all 2's, and that's a fold. I'm folding my and equals 2 function over a base case value of true. And I want to apply that to a list so I can determine, I want to take a list of Booleans and determine what that reduces to, right? If they're all true, then I should get true. If there's even one false, it'll be false, right? Because it's an and fold. So I wanted to write a proof for you of my factorial function. I wanted you to really believe me that every reduction step is the same, but without having to cut and paste all of them. So I created this neat little function, which I assume you have in your file, fact check. So this is a list, a really ponderous list of every reduction step that you saw above in the code file of factorial. And all I'm essentially doing is folding over that list a function that determines whether or not that particular reduction step equals 2. And if they all equal 2, then I get a list of trues, and then my final result of folding should be true. I hope that makes sense. It makes sense in my own head. I've not actually had to speak the words before. Raise your hand if that doesn't make sense. Seriously? I can try again. And that should work. Yep. So we're at the point now where we can start implementing the entire Haskell standard library if we want to. Range is convenient because it's tedious to make these lists. So let's say I want a list from 1 to 10. I don't want to type list element, list element, list element, list element. So I can just say range 1. I actually don't know if 10 works. It might blow up my stack. I forget. I don't even have a 10. Did I never define a 10? OK, I'll make a 10 real quick. 10 equals plus 5 and 5. And I prove it to myself that it works to array, lists. There we go, 1 through 10. So that's handy. I can index. So I take my list, and what is at index 0? Whoops. Yeah. Index list. Index 0 is 1. I can push elements onto the end of the list. I can append 2 lists together. This next one is a little bit more complicated. If you look at the Haskell code for the reverse function, it has a helper function. So actually, this code here is the helper function, and the actual reverse function is simply that function applied to some list x's. And again, you can verify that work. I have a feeling that if I try to reverse a list from 1 to 10, it's going to kill me. So I'm afraid. List equals range. I'll just try 1 to 3. To array int reverse. Oh, thank God. You try 1 to 10. better if your browser crashes than mine right now. So we have take, we have zip, zip with. We can start developing some pretty sophisticated things. I mean, you don't get this stuff in. I should stop making fun of JavaScript. It's not. I don't want to take cheap shots at JavaScript. The point is that you get so much more power when you have the reliability of these kinds of functions, right? And all of that stuff that we talk about in FP, referential transparency, currying, immutability. It's not like they're built into functional languages as features. They just fall out of the fact that this is the way this stuff works. I wouldn't even say it's the way it's implemented. It's just a property that it has that you just get.
I like to use it because that's kind of what's different about FP, I think, is that these inherent mathematical properties that are there whether you decide to construct or not.
Yeah.
And that's this exploiting essentially the way I can do the physics of the numbers or the iteration is.
Yeah.
You can do fuck it up for lack of a better word.
Yeah, and it is exactly so, right? It's not like Haskell implements monoids or whatever, monads. They just exist. They're there, and you can use them to do cool things, or not. My hope is that you will come away from this being able to show other people how to do this kind of thing. Use my code, come up with your own ideas. I'll show you the GitHub repo later for the whole thing. You can pull request me if you have. I want to actually develop this into a presentation for explaining to people exactly what you just said. Proving it to them. You have to prove it to people, right? Like talking convinces nobody. We have to prove it. So that's what I'm attempting to do. Yeah.
So, I'm a little bit of a noob on this, but so
Great.
is the type system an inherent part of functional programming?
No.
Okay, then I feel like the type system.
But I highly recommend using a language that has one.
Well, I feel like the type system, like in Scala or in Haskell, is a large part of this safety we're talking about.
Mm-hmm. So,
How to separate.
yeah, I mean, I'm not talking about type safety at all. Referential transparency you get, but that has nothing to do with type safety.
Okay.
So eventually doing this kind of programming will get so ponderous that you do want a type system.
Right.
I'm not going up to that point. I'm just doing like the basics, the fundamental particles really.
JavaScript has all that.
The LambdaConf is so light, right?
Pardon?
JavaScript has functions as first-class members of the language.
That's why I'm able to create all of this stuff, yeah. But no, you don't get type safety in JavaScript.
Okay, so is the limitation then just that JavaScript is clumsy?
I mean, that's not type safety, right?
Right.
Is it clumsy? I mean, that's a long conversation, right? It depends what kind of tool you want to use to do your job. I just think functional programming lets you express your problems. It lets you concentrate on the problem that you're trying to solve and not simply the language.
Do that in JavaScript.
Pardon?
I guess I'm saying, can't you do that in JavaScript?
Yeah, you could do anything in any language if you want. It just depends on what you want your quality of life to be. Sorry?
You can't have type safety in JavaScript if you want, right? You can't do anything.
No, I mean you can compute anything. I'm doing it right now, right? This is JavaScript.
They have type libraries for JavaScript.
Yeah.
Native to JavaScript.
Yeah,
Even with LambdaConf, you can implement a type.
you could.
You can start tagging types to this, and then
Yeah.
through this, I assume, you will be restricted on what you can throw into.
And I thought about it. I thought about doing some simple type system just to demonstrate that, but it's very complicated. I don't know if I could do it. I mean, maybe I don't think it would end up proving anything more about what I'm explaining. So let me just start to move toward wrapping things up because it is 10 to 12. I tried to put as many examples into the code file as possible because I did not think I would get through all of these things. So we have zips, we have list insertion, we have sort. I love this sort function. I mean, look at that. And this is not me. I mean, give functional programming some credit. If you have some basic elements like the ability to create lists and you have an insertion function and you have a fold, you can create a nice little point-free sort.
When you say point free,
No arguments. It's just composition. Yeah, sorry about that. Yeah, I'm not using any arguments. I'm just composing functions together to create a new function without specifying my arguments at all. Yeah, the other functions in that fold expression specify arguments. But I can leave them out because I've curried everything, right? I can partially apply one step at a time.
What is the point free? Like, that's the final it's like something that evaluates.
So the points are I mean, there's a good mathematical answer to that, but you can just think of them as the arguments,
Okay.
right? If I had, I mean, I could equally well write this function like this, and it would be the same thing. Sorry, I could write this, and it would work the same way, completely the same.
Yeah.
But I can factor out the x's, right?
And that is the point 3.
Yeah.
notation.
Yeah. It's not something that I would abuse, but in certain contexts, I think specifically with folds, it's nice to have. And that's once you get into functional programming, you can partake in these debates, and people do have opinions about point free and whether or not you should use it. I mean, I would say personally, this is just my opinion. I would tend not to use it because you lose some documentary value of having arguments.
Yeah, because you can name.
Yeah. I mean, I would lean toward not using it for the most part, but I like it.
Sometimes, I mean, I'm with you there.
Yeah.
For the most part, I don't, but sometimes you just make a little helper function in it.
I like them with folds because folds are like a well-known quantity.
Yeah.
So I think it's okay to leave them out in folds, but it's down to personal preference. So I can reverse that list and then sort it and get the same list, just to prove it to you. And this is kind of like a mini tutorial here, how you might turn Haskell take into these lambdas. I was going to have a few more exercises with drop and lm. You can create infinite lists. This is an infinite list of zeros. So you have streams. This is in all Lambda calculus, completely works. Try them out in your browser. Some demonstrations here of the universal properties of fold that I mentioned earlier, how you can turn many common recursive list functions into functions on folds. So this is a sum fold, a product fold. This is an example, right? I want the sum of a list. Oops. Oh, that's just that's proving it. So so I have a list 1 through 10, and I'm going to get the sum of that list, and this is just a nicer way to express folding the addition over the list, right? I just call it a sum fold, and I fold that over my list, and I get the answer. I can also, I can implement length that way, I can implement reverse that way, I can fold left instead of right, if you're familiar with fold L from Haskell, and that's slightly more efficient. The and fold and or fold I left as exercises. You can implement binary numbers using lists, and then you could do math on binary numbers. I didn't implement math on binary numbers, sorry about that. You could try that yourself. It might be a more efficient way of doing it using lambdas, but again, it's mostly for the conceptual enjoyment. Finally, trees, and if you can implement trees, you can implement graphs, whatever you want. I created a pretty printer for the trees so that you could see how they work, so I enjoin you to try that out, mess around with it. Let me know what you think. And then finally, if you are a Haskell geek, then this is a little section on how, in principle, you get a lot of algebraic structures from Haskell for free. Monoid, functor, applicative, some proofs, and of course, everybody's favorite, monad. So conceptually, you have a monad. It's not a proper implementation of one. It's not type safe or anything, but it works. Type all this stuff in. Prove to yourself that it works. This is what this looks like in Haskell. So compare the JavaScript syntax to the Haskell syntax. My pitch for Haskell: you can write all of these computations in a very clean, in very clean, easy to read code. That once you get the hang of it, it kind of just disappears, and then your thought process is revealed to you, and you don't worry about syntax quite as much. That is my feeling anyway. So one more fun thing that I'm going to show you before we leave. I made a joke about Fizzbuzz earlier. I actually implemented Fizzbuzz in Lambda calculus because I'm out of my mind. Here's what it looks like. So raise your hand if you've never heard of the Fizzbuzz problem. Okay, so maybe in a coding interview, just to see if you know how to code, you might be asked to implement a function that will take, say, the numbers 1 to 100, and it will return, what is it usually? I don't even remember what I did here. Fizz if it's divisible by 5 or 3. What is it? I don't even remember. Fizz if it's divisible by 3, buzz if it's divisible by 5, and fizzbuzz if it's divisible by 15, and then the number otherwise, right? If you can do that, then you should be paid $150,000 a year to write front-end apps in JavaScript. The next time you're asked to do this, you can show them my way of doing it. And I would like to give props to Tom Stewart, who wrote a book that you should all read called Understanding Computation. And I kind of stole this from him, although my implementation is a little bit different, and his is also in Ruby. Mine is in JavaScript, but you see what I did here? I need 15, I need 20, I need 100. I need the letters FIZBU, which I can just simply encode as numbers. Then I can create Fizzbuzz and Fizzbuzz. And ultimately, I get this function. And that's it. This is the Fizzbuzz function. And let's see. I didn't put it in the original file because I was having some problems, but let's see if I can. Also, the original version that I tried to do is meant to do this from 1 to 100, but it always blew up my stack, so I gave up. So let's try, actually, how did I should be able to do this on a list from 1 to 15. I hope. Bear with me if it doesn't work the first time. Okay. Oh, that's why. I need this function. Okay, to Fizzbuzz, special function, Fizzbuzz function, range 1 to 15 for my list. There it is. Did I pass the job interview? This is all in functions. I'm going to prove to you it's all in functions. Here's what it looks like.
Did you write that out one night, or maybe several nights?
I'm crazy. But look, it works. It totally works. Okay, I'm going to create my list equals range 1 to 15 just to make it a little bit easier. Okay. To Fizzbuzz. God help me. Oop. Get ready for your round of applause, or not. Ugh. I did something. I must have done something wrong. Oh, that's why. No, this is correct, right? 1 to 15. List. Oops. List 1 to 15. Nervous typing. To Fizzbuzz. Oh, you know what? I didn't do Fizzbuzz func, right? Fizzbuzz func expanded, which is all that stuff, applied to 15. What am I doing wrong? Okay, let me try.
Yeah, your auto-completion got rid of
Did it really?
the stuff that you wanted to type.
What'd it do? I'm gonna try.
You're missing a phrase.
I'm gonna try this again. Whoops. Okay. Doesn't like that. Okay. To Fizzbuzz. Fizzbuzz function. Wait, all that stuff, right? Applied to 15.
You don't need to give this expanded one the range?
Pardon?
This expanded version does not expect the range?
I don't know.
You're dangerously close to not passing the Fizzbuzz interview.
I don't know. Pardon?
Pass it list.
Oh, that's what I'm doing. God damn it. Still doesn't work. I don't know why.
It did some work.
Pardon?
It was doing work.
Yeah, list equals range 1 to 15. To Fizzbuzz. Oops. Yeah, to Fizzbuzz. Fizzbuzz func list. One final note, if you want all the codes, all of this stuff, it is here. Make a Lambda calculus. Most of the goodies are in this file. I haven't put everything there. I also have an implementation in Python, which is identical. It just has the word Lambda everywhere. And I'm going to try and create a few more. I hope you got something out of this. I wanted to have time for comments. If you see me in the hall, please give me feedback. But thank you very much for your patience. This is my first... This is my first ever tech talk. And I wanted to choose an easy topic, so I hope you got something out of it. Spread the good word to others, and thanks again.